Now, this is a little bit more application of that solution stoichiometry that we just did. This is something we do a lot in the lab, especially if you take Chem 162. We do what are called titrations. This is why we kind of talked about acids and bases a little bit earlier. Now, usually acid-base titrations are a 1-to-1 ratio, which kind of makes our calculations easy because the mole ratio is going to be 1-to-1. But titration looks like this, and you might have done one before in a different chem class, or you might not have, but you're going to have what's called a burette, and you're going to have down here an Erlenmeyer flask. And the whole point of a titration is to use something that you know the concentration of to find the concentration of something you don't know. Okay, so like I said, anytime you do acid base, this is our net ionic reaction. So it's usually a 1-to-1 reaction. So I've got my acid down here and my base in this again is called a burette. And then you have in here what is called an indicator. So an indicator is something that changes color to indicate that you have completely reacted them and you're at what's called the end point. So the end point is when you exactly hit that 1-to-1 ratio. It's when all of your unknown has completely reacted. And if you know how much of your known concentration was added, then you can calculate your unknown. So that indicator changes colors after you reach the end point. So the indicator in this case, most of the time we use phenolphthalein, which changes to this light pink color. That tells me I hit my exact stoichiometric ratio of 1-to-1. Okay, so endpoint is when they completely neutralize each other. Indicator changes color right at the end point or the equivalence point. The burette is what we use. We put our known concentration in this. This is the burette. We put our unknown down here in the Erlenmeyer flask with the indicator. And then the way that you read a burette is you like straight read it. You're going to practice this in the lab. It starts at 0, so it kind of tells you how much you added. And when you know how much of this you added, you can use it to calculate the concentration of this. So this is what we're going to do for titration calculations. Again, usually an acid with a base. So example 15 is for an acid-base titration. Now I know I got a lot of stuff circled here. Just kind of bear with me. Okay. So first of all, I said this was titrated. So I know I'm going to be doing some type of solution stoichiometry. I've got a reaction happening. It's probably acid-base. So I've got 2 milliliter sample of HCl of unknown concentration, so I don't know its molarity, is titrated with a 0.197 molarity sodium hydroxide. So I know the molarity of sodium hydroxide. If the sample of acid required 38.7 milliliters of sodium hydroxide to reach the endpoint, then what is the concentration of the HCl solution? So you'll notice I did some things in different colors. The HCl I did in red because that was the acid, and the sodium hydroxide I did in blue. So you need to read carefully. The 2 milliliter goes with the HCl, which I don't know its concentration. The 38.7 milliliter goes with the NaOH, and I do know its concentration. So I told you to always start with grams or milliliters. Well, if you have 2 milliliters, you would either have to do stoichiometry with both, but we can't, because I don't know the concentration of this one. So you want to start with the one you know the concentration of. So I'm going to start with this milliliters because I can convert it to moles because I know its concentration. Okay? I know this was a titration. I just wrote out my reaction. It's all 1-to-1. So I'm starting with this. I went ahead and put it in liters, 0.0387 liters. Well, since I know its concentration, I can convert to moles. So it's 0.197 moles per liter. That was this molarity. And it's a 1-to-1, so 1 mole of sodium hydroxide is with 1 mole of HCl. So I know that if I calculated 0.007624 moles of sodium hydroxide, that's also how much HCl was in there. Then I can find my concentration of HCl because I know it's moles and I know it's milliliters or liters from what I use for HCl. So 0.007624 moles over 0.002 liters gives me a molarity of 3.8 molar HCl. So really what we're doing here is a chemical reaction and using the stuff I know the concentration of, I know how much I use, so I know how many moles it was. So I use my mole ratio and then I'm like, oh, well, this also uses the same number of moles. I put those moles over those liters and get the concentration. Okay. I can also do if the total quantity of HCl was originally 2.5 liters, then what mass of HCl is present. Well, I've got a liters. I want to know a mass. Notice this is not a stoichiometry problem because I'm only talking about HCl. No reaction is happening here. So I've got the molarity from up here. I have my liters I'm talking about. I want to know how many moles was in there and how much mass. So I solve for moles and then converted that to mass. Okay. Now we can also do different types of titrations, like redox titrations. We'll do this in 162, but it's just a titration with not acids and bases, and this one is usually not a 1-to-1 ratio, but it works exactly the same way. So you do a titration, something that you know the concentration of, reacting with something that you don't know the concentration of. It's just a redox reaction instead of acid-base. A lot of the times we do this with potassium permanganate because it's purple. And when the stuff changes purple, that means I had extra in there and it's reached its set point. So it works kind of like an indicator. Okay, so this is a little bit more difficult than an acid-base one, but same principle. I've got 0.8890 gram sample of iron ore. What is iron ore? Well, that's where iron comes from. It's not pure iron, it's Fe, but it's got some other stuff in it. It's titrated to the endpoint with 47.20 milliliters of this molarity KMNO4. Now, first of all, I notice I have a milliliters that I have the concentration for. So I know I got to start with this. I notice I already put it into liters, and then I use that molarity, this one, pull it down here for my conversion factor to convert to moles. All right, before I even read the whole problem, I know I need to convert to moles from the thing that I have. Then I need to use a mole ratio. So it's wanted over given. Well, I started with KMNO4, which is 2, so 2 down here. Now, what am I trying to find? It says, what is the mass percent of iron in the iron ore? So the iron is what's going to react, right? I want to know how much iron, Fe, was in that iron ore. Well, what thing is iron ore? Well, if you look at this, I reacted the iron ore. So the thing with the iron in the reactant. So this thing has the iron in it. Now, I used this one over here because it's a reactant. Honestly, you could use this and put 10 or this and put 5. It would take care of itself over here in a minute, and I'll show you what I mean. So 2 moles of this produce 5 moles of this, a 2 to 5 ratio. Like I said, you could have picked this one or you could have picked this one. It's fine. And then I just want to know the iron part, though. This is a component within. Okay, so 1 mole of Fe2SO4. So every 1 mole of this has 2 moles of iron in it. So 2 moles of iron. This is, like I said, is a component within. I just want the iron part. And then I want to know the mass of iron. So I do 1 mole of iron with the molar mass of iron. So this is definitely a more complicated problem. Again, I told you could have used this one and done 10 here of FeSO4, and then this would have been a 1-to-1 ratio. So you can kind of see how that would have worked out. I just want the iron part. So if I calculate this, it gives me 0.295 grams of iron. And what that is the amount of iron, just Fe, that reacted in the whole thing. So that's all the iron there was. So if I put that amount over the starting whole iron ore times 100, it gives me the percent of iron in the iron ore, 33.21% iron. So this is kind of like what you would see in like a extra credit type question. This kind of encompasses a lot of things, and you have to know what all of the numbers mean. So good luck.